So to try and generalize what we just saw in the last video is we've got this pattern where if we can break a problem down into a sequence of events. Now, I keep putting the word events in quotation marks because it can be really, really broad what we consider an event to be. Just basically it's a thing, it's a part, it's a piece of the problem. If we can break a problem down into a sequence of those events, which is like what we did in the last one, right? Either pick your salad, pick your entree, pick your dessert, pick a first activity, pick a second activity, things like that. And then this sequence of events, we have the first event can happen in M ways. And then the second event can happen in N ways. And that would have to be the same number of ways no matter what happened in the first event, right? Like in the activity example, what that list of options might be might change, but the number of them stays the same, right? Dependent on, it didn't matter what we picked in the first one, the number of options stayed the same. And then say a third event can happen in R ways, and again, that would be the same number of ways no matter what happened previously. And there could be more of these, so I've just put a dot, 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 right? We could have a fourth event, a fifth event, so on and so forth. Then the pattern says the total number of possibilities for this sequence of events, for this original problem that we broke down into the sequence, is the multiplication of them. So M times N times R, and if there was more, we would just keep multiplying them together. This is the sequential counting principle, or sometimes I call it the general sequential counting principle, or just abbreviate it SCP. So on a lot of like written work, you might notice that I use that abbreviation SCP to stand for sequential counting principle. So that's the big picture of it, right? We're breaking the problem down into a sequence of things, there's multiple things happening in the problem, and we can figure out how many ways each of the things happens, and then multiply all of those numbers together. So let's look at a different example where event is going to be maybe not what we would have thought of based on the previous ones. This one asks, how many different 5-digit zip codes are possible? Like for instance, Sterling's zip code is 67579, right? We've got a string of 5 different digits to make up that zip code. We want to figure out how many total ones are possible. And we're going to see, can we use this sequential counting principle? Now, as a note that I'm going to introduce in this problem, I often, when finding that sequential counting principle, find it helpful to draw little blanks as kind of placeholders for the different events, and I label them to make sure that I know, well, really, what is that each of those stand for? And then we can figure out how many ways. So I almost mimic that up here with the little lines underneath, right? So this would be like our first event, and then second event, third event, so on and so forth. So let's think about in this problem, what are my events? Well, really, it would just be the different digits, right? I'd need to first pick a first digit. And once I've picked a first digit, I have to pick a second digit. And then I need a third digit, a fourth, and a fifth. So a third digit, fourth digit, fifth digit, right? If we think about it, the problem could be broken down into those steps. Pick a first number, pick a second number, third number, fourth number, fifth number, and you'll get your string of 5 numbers, and they are in order. Now all we have to do is think about how many ways can I do each of those? So how many options do I have for, say, a first digit? Now, one thing that's going to be helpful, and we will use some of these over and over again in this section, so it's good to get in the habit of something like a digit. Well, those are just numbers that are just a single numeral, right? Kind of like when we learned stuff in the past. So single numbers would be 0, 1, 2, 3, 4, all the way through 9. So don't forget 0 is an option for a digit. So when we count those, there's actually, right, 0, 1, 2, 3, 4, 5, 6, 7, 8 through 9. There's 10 options because we include 0. So even for the first one in the zip code then, we would have all 0 through 9 as possibilities. There are zip codes that start with zeros. If you go up to like Maine, they have zip codes that start with zeros. And then if we think about what comes next, well then for the second digit, well it doesn't even matter what I did in the first one, right? Something like Sterling's, right? 67579. You can repeat numbers. There's no rules. I could have a zip code that's 22222, right? You could have just all the same number over and over again. So there would also be 10 options for the second one because there's 10 digits, and 10 for the third, and 10 for the fourth, and 10 for the fifth. And then what we're going to do is we're going to use that sequential counting principle. Now that I've identified the numbers in the blanks, we look at, well, what does the principle say to do? It says to multiply them. So all we have to do is multiply all these numbers together, 10 times 10 times 10 times 10 times 10, which, if we multiply all of that together, is 100,000. So 100,000 zip codes are possible, 5-digit zip codes. Now, really think about, right? I don't want to draw a tree diagram for this, right? I don't want to draw a tree diagram that has 10 branches, and then off of each of those is 10 branches, and then off of each of those is 10 branches. I'm not going to list all 100,000 zip codes. It's not efficient, it's not practical, and it's also really unnecessary, right? That would take a super long time, whereas this was a very fast problem, a very efficient problem. So rather, this is the technique we're going to use. So we're not really going to use tree diagrams much in the future when we're working on problems. We're mostly going to use either this technique or some techniques we're going to learn in our next sections. Very, very occasionally, maybe you'll use one, or you might picture one in your head, right? In a problem like this, you might picture sort of what it looks like, and that might help you determine like how many blanks you need, how many events you have, and what numbers go in them, but we won't physically draw them. So instead, we're going to opt for this sequential counting principle. What you're going to do next is you're going to give a similar question a try on your worksheet. So try it first on your own, and then we're going to take a look at a second question on your worksheet where we are going to get to take a look at that question from the beginning of class. So there was those two motivating questions at the beginning of this chapter, right? We said, why is it hard to win the lottery? And why is it hard to pick the code on a combination lock randomly? By the end of this chapter, we're going to answer both questions, and we're actually going to answer the lock question next in the next video. So that's fun and exciting. So hop onto those videos, give questions a try though first on your own, see how this technique works on your own, and then use the videos to check yourself and if you need any hints along the way.